Very good. All right, so you guys asked about this number 24, yeah? There it is, the three-dotter. Started the assignment out with a three-dotter. Two in a row. 2 three-dotters in a row. Okay, this one is challenging, but you all have the tools to do it. So let's draw the picture first. I was going to say, I grabbed the wrong pen. Yeah, it's kind of hard to record this. All right, so number 24, we're going to say, alrighty, draw our oscillator and this little block that sits on top. Now, they give us a bunch of information. They say, little block has mass little m, big block has mass big M, the spring has a spring constant K, and what else do we know? We know that there is friction between the little mass and the big mass. And the coefficient of static friction is given. And we also know that this surface here is frictionless. Okay? And they're asking, what's the amplitude that's allowed here? If we pull this back a little bit, the little block stays on top just fine. If we pull this back too far and let it swing, the little block's going to slide off. Okay? The $10,000 question, because you could sit and look at equations for half a lifetime and you're still not going to get this problem right. You got to get the physics of it. So the physics of this is, if we put a block on top, a little block on top of the big block, there is an amplitude that will cause it to slide off. Why? Okay, here's a physical, unfortunately she can't see this, but if I put my little remote on top here and I let it go a little bit, remote's happy. It just goes back and forth without sliding. If I pull back too much, remote starts sliding around. Okay, so what we need to do is first figure out what's going on before we start trying a bunch of equations. So what's going on? How come a big amplitude causes it to slide around, little amplitude doesn't? Sir?
The friction between the two objects is causing the top object to accelerate when it's moving the other.
Oh, okay. So the top object is accelerating with the big object as it goes back and forth. And if there's too much acceleration, they start sliding across each other. And the other thing you said, the second part of your answer was it's friction that's causing the acceleration between the top block and the big block. You're shaking your head no. Okay, what's the matter?
It's the spring that's causing it. When you pull it back and you
Oh, great point. Okay, so when we pull this back, great point. Pull this back, the spring is causing the cart to accelerate. Okay? But I think where Trevor was going was, what's causing him to accelerate? So if I pull this back, that's too far. Let's pretend it doesn't slide. Don't have to pretend. It doesn't slide. What's the spring is causing the big block to accelerate. What's causing the baby block to accelerate along with the big block? Friction. Yes. So friction is what causes baby block to accelerate. If we have a bigger amplitude, do we have a bigger acceleration?
Yes.
Yeah. Because bigger amplitude means bigger force on the bottom block, right? Bigger force means bigger acceleration. Or, put it this way. Acceleration is negative x sub m omega squared cosine of omega t plus phi. Yeah, the bigger the amplitude, the bigger the acceleration. Now our maximum acceleration that occurs on the ends is going to be what? Take this equation and do what to it? Yeah, make the trig part of it equal to 1 or negative 1 and say x sub m omega squared. So the biggest acceleration that this thing goes through is equal to x sub m omega squared. So the bigger x sub m is, the bigger the amplitude, the bigger the acceleration. All right, so back to Trevor. He says the thing that's causing little m to accelerate is static friction. Is there a limit to the amount of static friction we've got? Yeah. Maximum static friction is mu times the normal force. Okay, what's the normal force on this little dude?
mg.
Yeah, we got mg down, we've got normal force up, so let's skip the Christmas rush and say it's equal to mu sub s mg. Okay. So how much acceleration can this force cause? How can I figure it out? How much acceleration can this guy create? What physics principle am I going to use to figure it out? F equals ma. Okay, that's where I was going. So we're going to say F equals ma, or mu sub s mg equals ma. So in other words, the friction force is the only force causing this guy to accelerate, and it's equal to ma. So why the maximum acceleration is mu sub s times g. Sir.
I should have done it your way, but I did it like, I calculated Fs max and then use it.
Yeah.
If you had to divide by the mass, what mass would you use? The total mass? The whole box?
Oh, in this case, we're looking at the acceleration of just this guy. Because friction isn't accelerating the whole thing. Friction is only accelerating the little guy, trying to give him the same acceleration as the big guy. As Amanda pointed out, the acceleration of the whole system is due to the springs. The acceleration of the little block, if you just look at him, that's due to friction. All right, so the maximum acceleration of the system is this over here. The maximum acceleration allowed by law for the little block is there. What do you think we're going to do? Yeah, let's set them equal, because we'd like to know what x sub m is. What's the maximum amplitude allowed, right? So I'm going to say, look, x sub m omega squared is equal to mu sub sg. Okay, so x sub m equals mu sub sg over omega squared. Oh, dang, we don't know what omega squared is. How can we find omega? What's the equation for omega? Square root of k over m. Do we know k? Yes. Do we know m?
Yes.
What m are we going to use? Brilliant. Why would we use the total mass, Jake? Yeah. It's like the acceleration, k, the springs, just like Amanda said, the k, the springs, are accelerating everybody, giving everybody this omega. So this actually has to be total mass down there. So I've got x sub m equals mu sub sg and the square of that. So I'm going to have the total mass over k, something like that. Is that right? Did
Yeah.
I haven't messed up too terribly? Isn't this a great problem? This is just a great physics problem. Because it forces us not just to, put things into equations. It forces us to really think about the physicalness, what's going on here. Okay, it's what separates math from physics. Is in physics you gotta, there's some kind of deep laws at work that have to be obeyed. Okay, so that's number 24. I'll leave the plugging and the chugging to you, but yeah. The other one that came up was 82. All right, in order to use the screen, I'm going to have to blank this out. Are you okay? You can actually just go look at the video too if you want and check it out. But I have to kill the screen here. So if you're not okay, say so now, because here it goes.
Steve, shut up.
Steve, shut up. Oh, goodness. All right. So 82 is not as terrible as this one. There's just one thing you have to notice on 82, and it all falls apart. So you'll be very happy by the time we get done with this one. It says we've got a massless spring, K of 19 newtons per meter. So we take a massless spring and we hang it up. And it's totally relaxed. It's a relaxed massless spring. It's just kind of hanging out here. K is 19 newtons per meter. We take a mass and gently attach it to here. And it's a mass of, I don't remember what it was, 0.2 kilograms or something. It was 0.2 kilograms. Okay? We carefully attach it there, and then we let go. And it drops. Whoa, and it starts to oscillate. And the first question is, how far is it going to drop? And at first it's like, what? How can we possibly figure that out? Now, if it drops and bounces back, how high does it have to go when it bounces back? According to conservation of energy, when it stops, it's got to have the same amount of potential energy as it had before. It's got to be the same spot. So it's got to bounce, come back, bounce, come back. In a perfect world, okay? In the real world, it probably won't go quite as high because of losses and all that business. But pretend we're in the perfect world, and this thing bounces and comes back to its original position. Where is equilibrium by definition? Half as far as, okay, that was going to be my next question. You answered my next question. What's the definition of equilibrium? Equilibrium is when what equals out? All the forces. So you already jumped to the answer here, Doc. There's going to be equilibrium, and then the furthest down it'll go is that same distance below equilibrium. So we've got amplitude here and amplitude. So I guess I'm saying if we can figure out where equilibrium is, we could figure out this distance here, which is what they're asking for. What's the drop distance? Well, the drop is going to be twice the amplitude or twice the distance from its highest point to equilibrium. And like you said, equilibrium is where the forces cancel out. So we've got like the spring force up, and we've got weight down. So I'm going to say, look, the spring force is K times X, and the weight is mg. So K times X equals mg. This thing just reset itself. That was weird. Or X equals mg over K. So in other words, this much force is causing it to stretch this much. Why? Because the K is that much. So 0.2 kilograms times 9.80 meters per second squared divided by, 19 newtons per meter. So it turns out to be like 1/10 of a meter, 10 centimeters. It's like 0.103 or something like that. Because I just did this last hour. .103.
That's the amplitude.
It is the amplitude, yes, sir. And so this drop distance is going to be 0.206 because we're going to double it. Okay, so that one wasn't as hard as you thought. As long as you first find equilibrium, and you remember conservation of energy says this thing's got to come back to its original position, then we're all set. The last part of this is the frequency. Because we got the amplitude, we already got part C done. What we need is the frequency. Remember the period, simple harmonic oscillator, 2 pi square root of m over k. So the frequency is going to be the reciprocal of that. That was weird. Okay. We got K, we got M. The frequency is easy. But the hard part was figuring out the distance of drop. Alrighty. 33. Right? Yes. Okay, we didn't do this one last hour. Let's see. A 10 kilogram particle undergoes simple harmonic motion with an amplitude of 2 millimeters, a maximum acceleration of magnitude of 8 times 10 to the third meters per second squared, and an unknown phase constant feet. What are the period of motion, the maximum speed of the particle, the total mechanical energy? What is the magnitude of the force on the particle when the particle is at its maximum displacement and half max displacement? Oh my goodness. They want everything in the kitchen sink, right? Goodness. All right. Start at the beginning. 10 gram particle. So mass of particle, 0.010 kilograms. Yeah? Point. All right. Simple harmonic motion, amplitude 2 millimeters. Hang on. 1, 2, 3. Yeah, 0.002. Very good. Acceleration 8,000. Wow. Okay, wouldn't survive riding on that thing. Unknown phase constant phi. May or may not bother us. Okay, what is the period of the motion? All right, well, period 2 pi square root of m over k, yeah? Got the mass, don't know the k. I guess we're screwed. Pretty much. So we're going to have to mess with this. The equation we've got won't work. Hey, what about acceleration? We have maximum acceleration. Remember, just from the last problem, the maximum acceleration is x sub m times omega squared, yes? So if we know x sub m and we know a, that means we can find omega. With omega, could we figure out the period? Yeah, because omega is 2 pi over the period. Or period is 2 pi over omega. So yes, we can do this. This means that omega is equal to the square root of a max over x max. So we can do this. It's 2 pi square root of x max over a max. Woo! We've got this thing. So that was part A. Period, under lock and key. B, maximum speed of the particle. Okay, our velocity equation is negative x sub m omega sine of omega t plus phi. So by now you know that V max is got to be what?
X omega.
X omega. Do we know X? Yes. Do we know omega? Onward. C. What do we want in C? I can't find it. Oh, the total mechanical energy of the oscillator. Total mechanical energy of an oscillator. We did that yesterday. It's like 1/2 k x of m squared. Shoot. Oh, but at the ends, that's when there's no kinetic energy. It's all potential energy. What if we were in the middle and it had all kinetic energy and no potential? That would also be the maximum, wouldn't it? So forget that. Let's say the total energy is equal to 1/2 m v max squared. Because we just calculated v max up above, and we know the mass. Bam! We win. Part D. What's the magnitude of the force on the particle when the particle is at maximum displacement? If you're looking for the force, what do you think we need to find at maximum displacement? We're looking for force. What number would be useful to have? The acceleration. See, for a man who didn't do his homework, you got this. Dude, you keep answering the questions. You're going to do them tonight, though, right? Yeah. All right. You don't have to work tonight. And the homework is actually really short tonight. So you can go back and... I don't get all the way through pendulums today. I get up to a point, and then I decided, okay, guys, we're just gonna hold off until tomorrow before I give the assignment. Otherwise, they're gonna have too much trouble with it.
What's the homework? No questions?
We did the
You didn't write it down, so we don't have it. No, I did the questions.
They didn't do the questions yesterday, so they're doing the questions for today. You guys did them for today.
Shut up, Steve.
Whenever I just point to him, just say that. So I'll point to him, and you just say, "Shut up, Steve." All right. So F equals ma, right? So we're going to say, okay, it's m times the maximum acceleration, and we didn't have to find the maximum acceleration, but we can find it, right? Yeah, we've got it. It's x times omega squared. So yeah, so we're good. So that would actually be like the maximum force. The hard one is part E. Because it's saying, all right, what's the force at half? Oh, no, it's not. Because when we're at half amplitude, this obeys Hooke's law, right? What's Hooke's law say? When you have twice the distance, you have twice the force. You have 3 times the distance, you got 3 times the force. If you got half the distance, you got half the force. I thought it was going to be complicated. It wasn't. Take your answer from part D and cut it in half. Yeah, it's proportional. I was all ready to do something crazy with the unit circle, and then it dawned on me. Okay, very good. All right, so new stuff today. Today is Pendulum Day. So, part 3. For some reason, over the past 20 years, it's become acceptable to say pendulums. You see it in books all the time, pendulums. It's like saying deers. Or mooses, thank you. Mouses. Yeah. It's not pendulums, folks, it's pendula. Plural of pendulum is pendula. Right. Or focuses. He's actually being helpful. Still needs a shave. All right. So the plural of pendulum is pendula. Now, here's the deal. We talked about this a bit last year. The story starts with Galileo in church. Now, Galileo had a kind of a rocky relationship with the church. The historians go crazy over it, and they're basically, the conclusion always is the church was bad because it didn't accept his findings, and they put him under house arrest and everything. It's actually not the truth. The truth is he was under house arrest because he called the Pope an idiot. So that's really what ticked the Pope off. I don't think it was because he thought that the Earth revolved on its axis or that there were objects out there that were not revolving around the Earth. I think what really got him in trouble was he told the Pope basically he did this big essay in which two people were talking. It's the dialogue of, I think it was just called the Dialogues. And there was two people talking, and one of them was himself, but he gave him a name like, Smart. And then the other guy, who was sort of supposed to be the Pope, he gave him the name Simplicio, which means, simpleton. And they were having a conversation. And then when he published that, that's when the feces hit the oscillator. Yeah. So I think sometimes the historians get it wrong. They always want to say, the church was anti-science. No, it was anti-disrespect, basically. And they were, it was pretty powerful at the time. All right, but anyways, you might disagree with that assessment, but anyways, Galileo's in church. And there is a censer on a chain swinging back and forth. And it's not censer with an S, censer with a C. It's basically a big pot full of incense that was burning. And this burning incense creates a pleasant odor. And as this thing swings back and forth, it fills the sanctuary with this pleasant fragrance. Now, he should be listening to the sermon. Might have gotten in less trouble had he listened to the sermon, but he was instead watching this thing swing back and forth. And he was timing how long it took to swing back and forth with his pulse. Didn't have a stopwatch, didn't have a watch. There were no clocks back then. It was before the mechanical clock. So he's timing this thing with his pulse, and he realizes that at the beginning, this thing has a pretty good swing on it. Later on, as the swing decays, he discovers that, wait, the time it takes for a swing stays the same. When it's swinging a lot, it takes, X number of seconds. When it's swinging just a little bit, it takes the same number of seconds. He said, this is cool. So he starts doing the math. Now, we've seen this before. When you have a simple harmonic oscillator like this guy on my track, it doesn't matter if it's got a big amplitude or a little amplitude. The time it takes to swing back and forth is exactly the same. You okay with that, Buck? This time is exactly the same as that time. If you notice, our equation for period doesn't have amplitude in it. The period of a simple harmonic oscillator, oh, there's my pen. Two pi square root of m over k. It's got mass in it. It's got the k of the springs in it, but it doesn't have amplitude in it. Doesn't depend on amplitude. Crazy. Okay. Now, so here's our pendulum. It's basically a string with a mass on it. Now, what he does here is kind of ingenious because he performs something called the small angle approximation. He says, for a very small theta, we're going to take this arc here and we're going to treat it like a straight line. Now, there's a difference there. Okay, if L is big, if the length of my string is big, there's a tiny, tiny difference here, maybe a few millimeters. So what we're saying here is not perfect. It's an approximation. Okay? It's pretty famous. It's called the small angle approximation. Another way of saying the small angle approximation, he's saying that the sine of theta equals theta. Well, it's pretty close to equaling theta in radians. Because sine is opposite over hypotenuse, x over L. And theta, remember the definition of radians is it's arc length divided by L. So if the arc length and that distance x are really close to each other, then that means the sine of theta and theta in radians are really close to each other. I also like to look at it this way, that it's also pretty close to the tangent of theta. Because the tangent of theta would be x over L, but not quite, right? Its L is just a couple millimeters too short. So x over L equals x over L. Pretty close, but not quite. Anyways, what are the forces on this little ball?
Gravity.
Gravity,
Tension.
tension of the rope. Tension of the rope will break down into two components. Here's our theta. This is Ft cosine theta. This is Ft sine theta. What force is trying to get this thing back to equilibrium? Ft sine theta. So I'm going to say the restoring force equals Ft sine theta. But on the y-axis, Ft cosine theta equals mg. So that means the tension equals mg over the cosine of theta. So that makes my restoring force equal to mg over the cosine of theta times the sine of theta. So I got a sine on top, I got a cosine on the bottom. Tangent is x over L. Now, forgive me for just a second. My force is this way, to the right. X is actually a displacement to the left. So I need a negative sign in there. So I'm going to say, look, my restoring force is mg negative x over L. And I'm running out of room fast. I'll rewrite it over here and clean it up. Okay, so my restoring force is negative mg over L times x. Question for you. If something is simple harmonic, the force, the restoring force, has to obey what? Hooke's law. Remember Hooke's law? F equals minus kx. The restoring force has to be minus a constant times x. Look down here at our equation for the restoring force of a pendulum. Yeah, See, so this is K. This is like the pendulum K, right? Which means that the period is 2 pi square root of m over mg over L. which means a little bit of rewriting here. We've got the period is equal to 2 pi square root of L over G. Check it out. The mass cancels out with a big wah. And I end up with the reciprocal of G over L, so I'll just call it L over G. All right, so pretty important equation for a pendulum. But there's a couple things about it we have to discuss. One thing, small angle approximation. What we said about the sine of theta equaling theta, it's true, pretty true for small amplitude, but if I do this, that equation's not going to work so well. The question I always get in the honors classes is, when does it break down? And my answer is always, how many sig figs you got? Right? So if you're at 40 significant figures, this isn't working either. Right? If you're at 3 sig figs, oh, you're fine. Okay? If you pull back here, 3 sig figs, you're going to be way off. All right? So small angle approximation. The other thing is, notice the period, in the period equation, the mass canceled away. It's gone. So I take this ball, I poke a hole in it, and I fill it with molten lead, and I let it harden, and then I swing it. What's going to happen to the period? Stays the same. Okay? I grab hold of this, I start swinging back and forth as long as my center of mass is right here. Swings back and forth, has the same period. I'll break the string, pal. It's just a little plastic hook up there. I would take it right down.
You took me the physics and figured it out. Yeah. So you would know.
Trust me, Steve, I know without trying. The string will break. Point, though, is mass doesn't matter, which is kind of weird. What does matter? Length of the string. Yeah, it's pretty clear. If we shorten the string, we shorten the period. It also depends on G. So take your grandfather clock, which works perfectly in Granville, and move to Boulder, Colorado. G is a little smaller. Suddenly your clock's not right. It's not only not right, it's taking a different amount of time for it to make one complete swing. It's like crap. So if you change locations, quite often you have to slide that pendulum on. It's on a slider. You have to make it longer or shorter so that the clock works right again. So if G gets smaller, you have to decrease the length of the pendulum slightly in order to keep the period the same. Or, the grandfather clock is just sitting in the corner looking pretty. All right. So, simple pendulum, pretty simple. There are other kinds of pendulums, though. Since we call these simple pendulums, simple pendula. See, I got to say it correctly myself. I've seen it wrong so often, I start saying it wrong. The other kind of pendulum is a physical pendulum. Now, a physical pendulum is not a ball on a string. It's the entire object. So you've got this pendulum. Or take a desk and, grab hold of the corner of it and let it swing back and forth. So if you have an entire physical object, not a point mass on a string, how do you calculate the period of that? If only it worked. We had that suggestion last hour. It'd be nice if you could say, okay, there's a center of mass. I'm going to make that L, stick it into the simple pendulum equation. Problem is, the shape matters. So if I've got a hoop here, that's a physical pendulum too. It's oscillating back and forth. If that had the same mass as this, even if it had the radius was the same as this, it would be the same because it's got a different rotational inertia. You called it, didn't you?
Oh, sure.
Oh, you said rotational inertia. Excellent.
Yes.
See, imagine what your grade would be if you did the homework. He's brilliant. Okay, so let's take a look at it. How would you do this? Okay. Let's say here's equilibrium. Try to do this without a ruler. And here's my big meter stick ruler thingy. So we pivot it right there. We pull it back. Some angle theta, and we let her swing. What's trying to get it back to equilibrium? Okay, let's say the center of mass is right there. There's mg. Because this thing has mass all the way down from the top to the bottom, we're not going to talk in terms of restoring force. We're going to talk in terms of restoring torque. So, we're going to take this mg and we're going to break it up into two components. Here's theta. So here's mg cosine theta along the length of the ruler. Mg sine theta perpendicular to the length of the ruler. The distance from the pivot point to the center of mass is called h. So the restoring torque is equal to negative h times mgh. I'm sorry, negative h times mg sine theta. Goodness, where'd that come? Okay, again, the reason for the negative sign is the displacement's to the left, the restoring torque is to the right. Okay, one rotation is one way, counterclockwise, the other one's clockwise, and so since they're opposite, we have to show that. This was on the AP test one year, and when I did the problem, I forgot the negative sign. I would have lost a point for that. Made me very angry. So I never forgot from that day forward. Okay, small angle approximation. In radians. Okay, rearranging slightly. This is the restoring torque. This guy here is the rotational K. And this guy here is the displacement. Now, with limited room here, I'm going to have to do this. Oh yeah, look at that. Got to make some room. Y'all remember the Great Divide? Translational, rotational. On this side I have X, V, and A. This side I've got theta, omega, and alpha. Over here I've got F equals MA. Over here I've got torque equals I alpha, and all that stuff. Well, check this out. On this side I've got restoring force equals minus Kx. On this side, I've got restoring torque equals minus mgh theta. Kind of the rotational K, mgh. On this side, I've got period equals 2 pi square root of m over k. On this side, I've got period equals 2 pi square root of, what's going to take the place of mass? Mass is inertia, rotational inertia. What's going to take the place of k? Obviously, mgh. So it's a little hand-wavy, but it turns out that the period of a simple, I beg your pardon, period of a physical pendulum is 2 pi square root of I over mgh. Okay, be careful. This I is the rotational inertia about the pivot point. So back to my big ruler here. We couldn't use the I about the center. We'd have to use the I about this point. So you got to use the parallel axis theorem a lot, in other words. Okay, so as this thing swings back and forth, we find its rotational inertia. We know h, the distance between the pivot and the center of mass, and we can figure out the t. How am I doing on time here? We go to 51? Okay. Oh, that's right. I always look at the wrong hour. 49. All right. So your job for tomorrow, you guys had the questions 5, 9, and 10 done. So your job for tomorrow is to get that challenge problem done. Okay? Challenge problem is due tomorrow. If you run into problems, give me a call. Please. So don't rush in tomorrow morning just before it's due and say, help me, help me.
We have 0 hour tomorrow.
We do, but we're going to be in the lab.
Yeah.
Dude. So we've got a cool lab to do tomorrow.
Like people couldn't be rushing because we'd already be in here.
Oh, that's true. That is true.
Are you gonna?
I'll collect them during the but still, have it done when you get here. I know it's your birthday.
It's right. It's today.
We forgot to say it.
Yes, I wish you happy birthday. It's your birthday too, isn't
Yeah.
it?
Steven, is it your birthday today?
Yeah.
Oh my God, it's
Oh my
Steven's
gosh, we
too.
didn't sing.
I'm not singing happy birthday. I'm
We had
sorry.
2 people.